Okay, kids, let's do some magnetic math. That's right, M&M. I said it, M&Ms. Ooh, M&M's so good. If you were stuck on a desert island for the rest of your life, the only thing you had to eat was one kind of M&Ms, boy, you get either fat or diabetes or a heart attack or all three. But anyways, I would probably go with the plain ones. The plain chocolate ones, my favorite. That one, the M&M ones are pretty good too, okay? You figure it out, you get back to me, let me know what you would think is your favorite M&M. Anyways, let's go through the equations. On the magnet outline, I had the equations written down for you, and I just said, we'll come back to these. Well, now we're getting back to them. We have to know how to use them. So here's the first equation we need to know how to use. And I always like to say F-bill, you know, F-bill. That's not very nice. Oh, Billy. No, Billy. I wasn't talking about you. That's Billy back there. You know, angsty Billy. Yeah, I'm not talking about you, Billy. But you said F Bill. I know, but it's just what the equation says, okay? Okay, I bet, Billy, you're not going to forget that equation, are you? Yeah. No, I'm not. I'm not happy. Okay, well, poor Billy. So F Bill is, well, what does it stand for? Well, F is force. So these equations are going to be about force. And remember, the second right-hand rule is about determining in what direction out of the palm or out of the knuckles the force on a particle or wire, as we will see. Because what's a wire? If you have electricity moving through a wire, it's a bunch of moving particles. So a bunch of moving particles are going to feel the effect as well as one single moving particle. All right, so here we have newtons. I'll do a unit analysis. This is the Tesla. The Tesla, yeah, named after that guy who invented the car. No, he didn't invent the car. They named it after him, you know, that smart guy, Tesla. Yeah. So anyway, Tesla is the unit. And Tesla is actually a Newton per amp meter. That's what a Tesla is equal to. So breaking this down, and this is current. We all remember current is amps. Current is measured in amps. And this is the length of the wire. That's an L. Length of the wire, which is going to be measured in meters. And so unit analysis says if we multiply those three things together, we will get newtons of force. Okay, kids. Now, let's make a drawing here. Now, if we have a particle moving through a field, and let's do a field to the right. Okay, here's my field to the right. That. Now, if I have a particle, maybe it's a negative particle moving up through the field. We use the right hand. Okay, we'll quick review. Fingers feel, direction of particle. It's moving in this direction. The force will be negative knuckles. There's a lot of my knuckles. And they both get at that end. And so the particle would go up to the field, and it would then be forced out toward you. Okay, that's a particle. What about a wire? What if we had a wire? And what's a wire? Just a bunch of particles, right? If they're moving, there's a bunch of particles moving. So let's say I have a length of a wire. It's moved, it's going through this magnetic field. So if there's a wire, and I have the current moving through the wire, so there's a bunch of particles moving in the wire. That's what what current is, a bunch of particles. Well, a bunch of particles are going to still feel the force just like one particle would. In fact, a bunch of particles will be a force multiplier. Yes, it will be. Look at this equation. If I have the length of the wire, the longer the wire that's in the field, the more the force is applied. Well, why? Because you don't just have one particle moving through the field, you have a whole bunch of them. That's going to multiply the force. That's the force on each particle. It's going to be a direct relationship with the amount of particles. The longer the wire, the more the particles are moving in the field. Also, current. The faster the wire, the faster the currents moving through the wire, what does that do? That puts more charged particles moving through the wire per unit of time. That's more particles is more force. So the faster they're moving and the longer the wire, the more force will be applied to that sweet, sweet wire. And this is the strength of the field in which we are moving the particles through. So, for example, if we had this length as being 1 meter, 1 meter of length, and the current is 1 coulomb per second, aka, all the cool kids, 1 amp. So that's 1 amp. And the strength of the field is 1 Tesla, which is a Newton per amp meter. Now let's do the math, kids. Come on, you can do this without a calculator, I hope. 1 times 1 times 1, anyone? Billy. 1. Very good. See, Billy, he's still hanging in there, even though we said F Bill. So that is 1 Newton of force would be applied to that wire as the electrons are moving. Now, here's the thing. We have to remember, we don't have to actually. The right-hand rule takes care of this for us. Let me show you something. So you know, or you should, that the direction of I is the direction that positive particles would move. And so you might be saying, all right, okay, all right, what would be the force? What direction of force? We know the number of force, 1 Newton, but in what direction would that force be applied? We have to know how to do this. Second right-hand rule, okay, current is this way, fingers field this way. So now we have to remember, the direction of current is the direction that positive particles move. So positive, palm, into the board. This wire would feel a force of 1 Newton pushing it into the board, okay? But you might say, well, wait a minute. These are electrons that are moving. And because electrons go in the opposite direction of the way that current is defined to move. I remember that from the last unit. Very good, Connie. Thank you. Okay, all right. Now, here's the thing. So let's use our right-hand rule now and see what happens. If I think through and say, all right, well, I know the electrons are actually doing the moving in a wire, and they're the opposite direction that the I direction is, so it'd be down. So down, fingers field, negative knuckles, still into the board, right? It'd be still into the board. Negative goes down this way, opposite the I, fingers field, into the board. All right, we don't actually have to think about it. I mean, it's good that we thought about it, but we don't have to think about it to get the direction of the force being applied. We can just go ahead, use our right-hand rule. Okay, we'll just say, okay, they're moving this direction, and it's going to be into the board, palm positive, because that's the way these move. Or if you wanted to, say to yourself, I'm going to go with the electrons are moving this way. I'm using my right-hand rule, negative knuckles. Still going to be into the board. Okay, either way. Yeah. Okay. So that is, one other really important thing. This equation, and you should see it, and it better be, it is. Written on your AP handout for equations, should have a sine angle theta there at the end. That's not a good marker. Sine theta at the end, it should. And why is that? Okay, so let's go back to the problem that I just had here on the board. Now I got my wire going through here. That's 90 degrees, okay? That's 90 degrees. Look at that. 90 degrees. So the wire is 90 degrees to the direction of the field. And that is maximum force. At 90 degrees, maximum force is applied. So if you were to put 90 degrees in here, you kids all know the sine of 90 degrees. Yeah, do it now. 1, okay? And that gives me a maximum force. So this equation is set up for the maximum force that something, a particle or wires, or particles in a wire, is going to feel. Now, well, what if the line, though, the wire is not at 90 degrees? Oh, okay. Well, what if you put the wire, or a particle, in fact, this works for a particle as well. You put the particle or the wire, here's the wire, in it, so the current is moving here, parallel to the force lines. So now what's the angle here? Well, it's 0. There's no difference in the two lines, so it's 0 degrees between the wire and the field lines. So put a 0 in there, what do you get? Nothing. You get nothing. So between here and there, you get minimum and maximum force applied to the wire. That comes in handy, really important handy-dandy notebook when we start talking about generating power in a power plant and those electromagnetic generators and what they do and how they do it and why current alternates back and forth. This is all going to come into play, kids. You're going to have this big light bulb go off in your head and go, not in your head, hopefully, above your head. Wow, you're so smart. You'll be like, whoa. But for now, let's just stick with, what was I just babbling about? I don't know. But what if you had a wire that was somewhere in between parallel and perpendicular to the lines? So now I would have to measure this angle here. That's my theta angle. Remember, theta here is 90, theta here is 0, so you'd have to measure from here. So 0, boom, 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 90. So whatever this angle is here, that goes in here. So if this is 50 degrees, all right, we put sine of 50 in there and then multiply by these 3 factors. All right, so that is, most of the time though, the vast majority of the time, not always, but 99.2%, I've done the math. you're going to have this at 90 degrees, because usually what you're interested in, and we're going to see soon in the real life application of generators in a power plant, you want to know what the maximum amount of stuff you're going to get. Not the, you don't care about the minimum, 0, but the maximum is what you want to know. Okay, in between is like in between, but you want to know the maximum. So that's usually what you're going to end up doing. And usually this will be at 90 degrees. So you can just go ahead and multiply that by 1. That's why a lot of times I just write it like this. I got to remember, oh yeah, it's not at 90 degrees. You got to do that sine angle thing. Okay, don't forget that. Okay. All right. So now you'll have one of those in your homework set. Yes, you will. Yes, you will. Okay. One other equation that we have is for force is F equals BQ. F equals BQ. BQ. This is BQ. It's French. Okay, it's French. Yeah. And so this is a very similar equation as F Bill. Stop saying that. Sorry. Jeez. I keep forgetting Billy's in class. And so F BQ is for a particle, not a wire, a particle. And so with one single particle, well, it could be a couple of particles, and then you'll just take this and multiply it by how many particles. Like you get 2 particles moving through a field, and you would say 2 times this. But typically that's not the case. You have one particle, and you want to know the force on that particle. So again, it's the strength of the field. Ooh, what's that? You remember. Da-da-da-da-da-da. Charge. Yeah, coulombs, and this is how fast that they are moving. And so that force, and remember what this is. This is a Tesla, and a Tesla is a Newton per amp meter. So if you multiply by coulombs, okay, so coulombs, and this is going to be meters per second. We're doing a little unit analysis, kids. I love it, love it. Oh. And so meters per second. So we end up getting, and remember, a coulomb per second is an amp. Boop, 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 and a meter boop, boop, cancels. You get newtons. So this is for one particle. The charge of the particle. So what happens if you have a neutral particle? Huh? What if you're Switzerland? What if you're Sweden going through there? Okay, ain't nothing going to happen to you. You got to have some charge, either negative or positive, in order to get that. Now, so a positive or negative in terms of the actual magnitude of the force won't matter. If you have a negative force, that means you had a negative particle going through. If you have a positive force answer, you get a positive particle going through the field, the magnetic field. So this is how fast. Ooh, so the faster it goes, the more force it feels. Remember the wire? I talked about the wire, where the faster the current is going through the wire, the more particles are subjected to that field. So the speed increases the force. Direct relationship. And so what if you're not moving? What if you're just kind of chilling, hanging out in the field? You know, chilling like the villain, hanging out in the magnetic field. Here I am. Oh, I'm a positive particle, all right? I'm a proton. I'm not an amateurtron. I'm proton. Yeah, I'm hanging out. It's funny. Oh, what if you're just a proton hanging in the field? Nothing. You're not moving through the field. You have to, in order to move, you create a force, you create a field that's a magnetic field around you, and you have to have interaction between these 2 fields. And so without movement, you don't create that. There's no interaction. Nothing. You gotta move. Keep it moving, people. Keep it moving. And you gotta be charged. All right. So if you have those 2 things, you'll get yourself a. And this equation also, this is for a particle, also has that sine q at the end. Oh, sine q. I'm looking at the q. Sine theta, same thing. Usually you want to know the maximum force, so usually it's going to be 90 degrees, so usually this is irrelevant, but not always. So if I have my particle, so I've got a field like this, and I have a particle that's moving through the field at an angle. Right? So this would be maximum, that's 90. This is minimum, that's 0. So this is maximum. So, well, where's the theta? Okay, where's the theta? Is the theta measured from here, or is the theta measured from here? So let's say this is, you just say this angle here is 50 degrees. So that's 50 degrees. That would make this 40 degrees here. Okay, which angle is your theta? Well, that is 90. That gives you maximum. This is 0. That gives you minimum. So that's 45. So which one's theta? It's measured from the minimum. So the theta in this example would be 40. It's measured from the minimum force. That would be 0, and then we build up to 90 maximum. So we would go at 40 if we're moving through here, and that's 40. The 50, we use the 40. So it's measured from the direction of the magnetic field. And that's the easiest way to remember it. The theta is measured from the direction of the magnetic field. You measure it from that. Okay? All right, 15 minutes. I got to shut this down. I think that's it for the force equations. I have another one I have to do for you. This is really important, but those are the two basic equations, and I think that'll wrap up our basic equations. That will get you through most of the homework that's due on Friday on magnetism, but not all of it. We need another video.